Hello again everyone, welcome back to ptet.chemistry channel. So in this new section on topical multiple choice questions, this is section 10.4. It's just my category for this halogenoalkane chemistry. So RX kind of chemistry, halogenoalkane. So this is asking you to identify compound X. So we know that this aqueous NaOH and reflux is an indication of hydrolysis. Hydrolysis of the CX, the carbon halogen bond, and you would form COH, essentially an alcohol. And then this thing there, together, they have to come together because the dichromate, this is called a dichromate 6, we use it to oxidize alcohol, and it has to be together with an acidified species in order for the redox to work, which you would have done in your redox topic as that, because it will go from orange to green, which is Cr3 plus aqueous plus H2O. So there's 14 there, and there's 12, should be 6, I think. It's 12 minus 6 is plus 6, yeah. Okay, so that equation is balanced, and you need the acid, otherwise this redox will not work. Anyway, this is not asking on that. I hope you realize that we should have done oxidation of alcohol first. All right, so when we oxidize alcohol, we can get carboxylic acid, aldehyde, or ketone, but here you can see there's only one oxygen. What I can tell is it is not carboxylic acid. All right, if it is not carboxylic acid, therefore I'm looking at primary alcohol. Sorry, no, I'm not looking at primary alcohol, I'm looking at secondary alcohol only. Okay, so because tertiary alcohol cannot be oxidized, whereas a primary alcohol, if you don't distill it, we are assuming it must be reflux then, because if we don't distill it, we're supposed to get carboxylic acid if we oxidize primary alcohol. Only one oxygen, must be ketone. All right, so this one must be ketone. All right, therefore it must tell you it's secondary alcohol. So think about 4 carbon alcohol. So 4 carbon alcohol, it must be a secondary alcohol. Well, it could be that. If you think it is that, it is not butane 3-ol, because you want the lowest number. So again, these and these are exactly the same. These are called butane 2-ol, because you want the lowest number for the OH. Right, 4 carbon in the longest chain. There's 3 hydrogen here, because this is skeletal formula. Show carbon form 4 covalent bond. So we don't show the hydrogen bonded to the carbon. The hydrogen is bonded to the oxygen, so we show it. So there's 1, 2, 3 hydrogen, because the carbon is bonded to one other carbon. This carbon has formed 1, 2, 3 covalent bond. There's 1 hydrogen there. There's 2 hydrogen. There's 3. So 3 plus 2 is 5, plus 1 is 6. 6 plus 3 is 9, plus 1 is 10, C4H10O. This is a secondary alcohol because the carbon with the OH is bonded to 1 and 2 other carbon. The carbon with the OH is bonded to 2 other carbon. This is secondary alcohol. So that is your C4H10O. When you go backward, so what is the hydrolysis then? The hydrolysis convert the CBr into COH with the use of aqueous NaOH. Okay, so I've done it backward, but if I go forward, it's aqueous NaOH and reflux. That is your hydrolysis reaction. And the name of it, this is a secondary halogenoalkane, because the carbon bonded to the halogen is bonded to 2 other carbon. In terms of name, again, we want the lowest number for the halogen. So this is so that just now was butane 2-ol. This one is a 2-bromo butane. So the halogen group comes in front as a prefix. The alcohol group comes at the end as a suffix. All right, so that is 2-bromo butane. Just to recap, the oxidation of the alcohol give you a product with only 1 oxygen. It cannot be aldehyde because we are not distilling it. We are just heating, which means reflux in this case, because we are not distilling it. It cannot be tertiary alcohol, therefore it has to be secondary alcohol, giving you only 1 oxygen, must be ketone. There's only 1 secondary alcohol for 4 carbon alcohol, and they are formed from this hydrolysis reaction. So going back to the pre-hydrolyzed product with the bromine, and therefore you could name the product. All right. So actually I stand corrected. I might actually make all of this 10.5. So 10.4 will be the alcohol topic. It seemed better like we have done alcohol before the halogenoalkane. All right. So I'll change that to 10.5. So 10.5 will be my halogenoalkane now. All right. 10.5 is halogenoalkane. So this next bit is talking about chlorofluorocarbon. So they're saying which of the following will not destroy ozone and therefore can be used safely. So we are looking at something with very strong C halogen bond, because if you have very weak carbon halogen bond, they can break easily to give you free radical, right? So will not destroy ozone. In fact, very strong C halogen bond, all of them contains halogen. This is the only one that has no halogen, and they want it as a replacement, right? So despite how strong the CF bond is, can you see you also have CCl, you also have CCl, and you know CBr can break easily as well compared to CCl. So when they break, they can give you free radicals, they can destroy ozone. But this one has no halogen at all. This is a hydrocarbon. This is butane, a 4-carbon alkane, butane, no halogen, is the safest replacement. All right. So again, I'll change that to 10.5 as halogenoalkane. So this is talking about which free radical is most likely to result. This is in continuation of what we did in the previous question. We are looking for the weakest carbon halogen bond. So what do you have here? Okay, you have a C, a H, a F, a Cl bonded to a carbon, a fluorine, and Cl. I hope you can tell carbon chlorine is the weakest of all. Okay, which means which free radical is most likely? Well, that means you will break the carbon chlorine the easiest, because if you compare in the data booklet, that and that, those two are so much stronger than a CCl. So this is the easiest to break. When you break it, you will break it by homolytic fission. This was a term that is stated in the specification under introductory organic chemistry. So you need to know what is the definition of homolytic fission that will give you the free radicals. Yeah. Okay. So I have to lose a chlorine. I have 2 chlorine to lose. So if I use a different color, okay, if I use a different color, then I will get CHFCl, CFF. I'll get that after I lose the chlorine. And if I do the one in pink, I will get the radical there, like that. Okay. So what we have here is, you see the 2 chlorine are still around. The 2 chlorine are still around, so that's not good for you because you haven't broken the thing, yeah? The 2 chlorine are still around. There's only one answer then, okay? And this one happens to be this. So both are possible answers, all right? So this could be a last 10 question, as in which of the following are possible, or which of the following are possible from the irradiation of this compound. Both of these are possible. You are breaking the weak carbon chlorine bond, yeah? But of course, there's only one answer here because all other 3 options that are incorrect, they still have the 2 chlorine in them. So basically, you haven't broken the weakest carbon halogen bond yet. In this question form, they're asking for what is the best synthetic method, yeah? So let's think about 1,2-dibromo-3-chloropropane. So they have abbreviated it as DBCP, but we got to know from the name how to draw it. Propane, 3-carbon straight chain. Propane, 3-carbon straight chain, yeah? Okay. So actually, I'm going to draw skeleton. Okay. 1, 2, 3. I have a 3-chloro. I have a 1,2-dibromo. So I have 2 bromine, 1 at 1, 1 at 2. So that is my 1,2-dibromo, 3-chloro. Okay, bromine B before C. So that's why you want the lowest number for the bromine first before the chlorine. All right, 3-carbon straight chain. what is the best synthesis for this compound? Okay, what's the best synthesis? If you look at A, so this is target, this is what you want. If you look at compound A, you will have CH3, CH2, CH2, Cl, and then plus Br. Well, I hope you can see that this is not a carbon-carbon double bond, because CH3, CH2, CH3, CH2 carbon form 4 bond. A is not good. If this is double bond, then yes, alright? A is not good. As a matter of fact, I think we saw it already. If you look at C, that is the one, CH2 double bond, CH, CH2, Cl, and then you could do electrophilic addition, which you learn under hydrocarbon organic chemistry. You could get electrophilic addition just like that, and that is your target compound. Okay, so C must be correct. If I just look at B, you have the same problem again. You have the same problem because I'll show you why. Okay, if you look at B, you have that and you have that, and you want that to produce HCl plus your Br and Cl. Why is that not good? Because that is free radical substitution. In a free radical reaction, are you sure that this will be 100%? No, because it's a chain reaction. I hope you know radical reaction, something called chain reaction. You do not just produce one product, the yield is going to be quite low. Whereas here, you only produce one product, Br, okay? Because this is not free radical substitution, it's electrophilic addition. They want the best method, alright? So this is very hard to control because it's a free radical chain reaction, and also very low yield because you can produce other product as well. This is PBr5. We use it to brominate alcohol or the OH of a carboxylic acid. You don't do that on a carbon-carbon double bond, okay? There's the wrong chemistry there, alright? So we did say earlier, 10.5 will be our halogenoalkane chemistry, alright? So this is the last question of this halogenoalkane series, category 10.5. The release of which of these gases causes the greatest depletion of ozone layer? Okay, so we know free radicals can deplete ozone layer. So how can you get free radical from these? You must break the weakest carbon halogen bond. Alright, so here we have no CX, so it will not deplete ozone layer. Alright, here we also have no carbon halogen bond, so it will not deplete ozone layer. Here you have a carbon halogen bond, but you have CF bond only. Of course, you also have CH and CC, but we're looking at carbon halogen bond because we want to generate the free radical, species with unpaired electron. Here you have CCl and CF. The CCl is weaker. Therefore, you will break the weaker bond because it requires so much less energy to break, so why wouldn't you break it? Therefore, that is the one that will give you the chlorine radical that can deplete the ozone layer. Fluorine radical would mean you need to break the carbon-fluorine bond, which is stronger than that and require a lot more energy. Alright, so that's the end of this 5-question series on halogenoalkane section 10.5. If you enjoyed these videos, please subscribe to the channel, and I'll see you in the next video. Alright, share with friends and colleagues and students.